In the last section, we just dealt with the general sine and cosine curves. Remember, this is just one period of the graph. You need to know that even though we don't show it, the graph continues on in both directions. Well, now we're going to start making some changes to the graph, and I'm going to compare it to something that you've done before. One of the things you did in Algebra 2, and you spent quite a bit of time doing this, was taking functions, parent functions, and then multiplying it by a number. Well, do you remember what multiplying x squared did to the parabola? We say that it stretched it vertically. And then if we instead multiplied by 1/2 instead of 2, we say that it compressed or shrank vertically. It depends on which teacher you had on what they called it. We're going to do the same thing with sine and cosine curves. We're going to stretch it vertically or compress it vertically. So if I want to graph 2 sine of x, multiplying it by 2 would change how high and low it goes. So instead, it would go up to 2 and down to -2. This is called changing the amplitude. The amplitude is how high and how low a graph goes from some line that goes down the center of the graph. The formula that the book uses is a little bit different from the one that I'm about to give you. The amplitude, which I want you to notice is in an absolute value bar because it's a distance and we're never going to say it's negative, is the maximum minus the minimum divided by 2. So if you look back at the original sine function, the one in black, the maximum is 1. The minimum is -1, and 1 minus -1 is 2, and 2 divided by 2 is 1. The amplitude of the original graph is 1. The red graph, 2 sine theta, is going to be max minus min divided by 2. Well, 2 minus -2 is 4, and 4 divided by 2 is 2. Why would you have to use that formula? Well, you would only use it if you were given a graph, but not an equation. From the equation, we're going to be able to tell you what the amplitude is by looking at the number that the sine or cosine curve has been multiplied by. So we're going to start with this. This is the first change, transformation, that we're going to perform on the parent functions sine x and cosine x. And don't worry, the other transformations are coming. All right, this one is slightly different from the one I just talked about. In example 1, we want to state the amplitude for the function y equals -2 sine theta. Remember I said the amplitude is the number that gets multiplied in front of the parent function. It's the absolute value of it. The amplitude is 2. But that negative is significant, and we'll come back to that in a second. In part B, we want a graph. Y equals -2 sine theta and y equals sine theta on the same set of axes. All right, let me start with the first graph, which is y equals sine theta. So y equals sine theta oscillates between 1 and -1. Its period is 2 pi. So that means the middle is 1 pi. This is pi over 2, and this is 3 pi over 2. The graph always starts on the x-axis, and then it goes up, middle, down, middle. All right, now let's talk about this negative. So let me go back to something you do know. Let's go back to our favorite y equals x squared. What happened when we multiplied the parent function by a negative? Well, it took that parabola and it reflected it over the x-axis. So not only is this graph going to go between 2 and -2, but it's going to flip it over. So think about it. What happens when it reflects over the x-axis? instead of the graph starting at 0 and then going up, middle, down, middle, wouldn't it go down first? So it's going to start at 0, and then instead of going up, it's going to go down to -2, middle, up to 2, middle. So not only did I stretch it vertically, but I also reflected it over the x-axis. The same rules that applied for transformations on functions in Algebra 2 are going to apply here when we talk about the graphs of sine and cosine. What I do want you to notice about these two graphs is only the amplitude changed, and it reflected over the x-axis, but it hit the x-axis at the same location, so the x-intercepts did not change. Neither did the period. It still went between 0 and 2 pi. And again, remember there's more to this graph. We're only ever going to graph one period of the graph because that's all the information that I need in order to get a sense of what's going on. This was a transformation that we didn't really focus on or even test you on last year. It's hard to see this particular transformation. It's a lot easier to see it with sine and cosine functions or any other periodic function. But if instead of multiplying the output by a number, you multiplied the input by a number, that stretched and compressed the graph horizontally. So multiplying by 2, we say compressed horizontally, and if you multiplied by a number bigger or between 0 and 1, we said that it's stretched horizontally. Like I said, it's going to be a little bit easier to see when we do this for sine and cosine curves. So what we're going to do is we're going to call stretching and compressing horizontally a period change. So now for the equation y equals sine k theta, where k is the number getting multiplied by the input, or y equals cosine k theta, makes no difference. The period is going to be 2 pi divided by k. So let's look at a period change with a cosine function. State the period for the function y equals cosine theta over 4. The question is, what number is being multiplied by theta? It's not 1. And I know you want it to be 1. It's actually 1/4. So in this case, k is 1/4, so the period is 2 pi divided by 1/4. When you have a fraction within a fraction, you have to multiply the numerator by the reciprocal of the denominator. And it turns out the period is 8 pi. That means that it's going to go 8 pi along the x-axis before it repeats its pattern. So now in part B, when we go and graph that, the amplitude is 1. I'm going to make 8 pi be out here. So in between is 4 pi. So here is 2 pi, and then this must be 6 pi. Since it's a cosine graph, the cosine graph, one period, starts and ends its period at its maximum. In the middle, it hits its minimum. And in between the minimum and maximum, it hits its x-intercepts. So remember, this is really only one period. So then what would one period of cosine theta look in comparison to this? Well, remember, cosine theta only has a period of 2 pi, which means that its graph would start and end at its maximum, middle would be minimum, and in between would be its x-intercepts. So that would be cosine theta. Look what happened when we changed the period to 8 pi. We stretched it out. Think about it like a rubber band. We just kind of took it and stretched it out. If you want a better comparison, remember that it repeats itself every 2 pi. So it would look something like this inside that red curve. Now let's put amplitude and period together and graph it. State the amplitude and period for the function y equals 5 cosine 2 theta, and then graph the function. All right, let's start with the easy part. The amplitude is 5. That means instead of going up to 1 and down to -1, it's going to go up to 5 and down to -5. The period is 2 pi over k. Well, in this case, k is 2. 2 pi divided by 2 is 1 pi. That means I've shortened the period. The graph is going to repeat itself faster. So now let's go to the graphing part. How am I going to graph this? Well, the way that I like to graph it, and I like to make a very cheap graph, I do this. I make a tick mark here, I call it 5. I make one down here, I call it -5. Notice that I didn't make 5 tick marks. If you really need to make 5 tick marks, you do it. The next thing I'm going to do is I'm going to put a tick mark well out here. I'm going to call it 1 pi. So my graph is going to start at 0, and it's going to end at 1 pi. And since it's a cosine function, it's going to start and stop at its maximum, and somewhere in the middle it's going to hit its minimum. Well, what's between 0 and pi? Well, half a pi, right? And then in between those, it's going to hit the x-axis. But I got to do one other thing so that Mrs. Friedlieb gives me all my credit on tests. You have to label those 2 additional tick marks. So, what is halfway between 0 and pi over 2? It may help you to think about it this way. Remember, this is 90 degrees. Half of 90 degrees is 45 degrees. What's 45 degrees in radians? It's pi over 4. And then, what's halfway between 90 and 180? It's 135. What's 135 degrees in radians? It's 3 pi over 4. I'll give you another way of looking at it. This is 1 pi over 4, so the next tick mark must be 2 pi over 4. So this is 3 pi over 4, and this must be 4 pi over 4. But notice 2 of those tick marks needed to be reduced. So what we're going to do when we graph these trig functions, you only have to graph 1 period. You will have 5 tick marks. There are 5 tick marks because the first one here is 0. You're going to have your start and end of the period and the 3 tick marks in between, which are always evenly spaced. We may need to talk about how to find those. They're going to be very easy because they're all averages. Let's go the other direction now. What if I tell you the amplitude and period, and I want you to determine the equation? So first of all, it says the amplitude is 2. We want to write a sine function, and the period is pi over 2. So I know I'm going to write the equation y equals a sine k theta. Here's the problem with the amplitude. The amplitude is an absolute value. So I don't actually know if the equation starts with +2 or -2. Because of that, I'm going to write plus or minus 2 at the beginning. The next thing I need to do is find out what k is. K is not pi over 2. Remember, the period is equal to 2 pi over k. Oh, I have a proportion. I know how to solve that. Pi times k is equal to 4 pi. Divide by pi, they cancel, and I find out k is 4. So this is 4 theta. I'm going to repeat this again. The period is not k. One of the most common mistakes that students make when they write the equation being given the period and amplitude is they really want pi over 2 to be k, and then they don't have to do any work. All you have to do is set the period equal to 2 pi over k, and it's a proportion, and you're all very good at proportions now. Many real-world situations have periodic characteristics that can be described with the sine and cosine functions. When you're writing an equation to describe a situation, remember the characteristics of those sine and cosine graphs. If you know that the function value when x equals 0, or you know the function value when x equals 0, if you know if it starts at 0 or at 1 or its maximum, and whether the function is increasing or decreasing, you'll be able to choose the appropriate function to write for the equation. So let's do a real-world application problem with a pendulum, something we should have looked at in physics. A pendulum swings a total distance of 0.30 meters. The center point is 0. It completes a cycle every 2 seconds. Assuming that the pendulum is at the center point and heading to the right at t equals 0, find an equation for the motion of the pendulum. First of all, make sure you know what a pendulum looks like. It looks like something dangling, and then you kind of swing it back and forth. So it swings this way, it swings this way, but it always passes back through equilibrium. Now, there are a couple things in here. They didn't use the words amplitude and period. Well, if they didn't use those words, how am I going to find them? Okay, so let's start with this. The pendulum swings a total distance of 0.30 meters. That means this is 0.30 meters. The amplitude is going to be half of it. All right, so now I know the amplitude. So it swings 0.15 meters one way, 0.15 meters the other way, off of equilibrium. The other thing it told me is that it completes a cycle every 2 seconds. Well, completing a cycle is code word for period. So now, if I know that 2 pi over k is equal to 2, that's a proportion that I can use to solve for k. So 2k is equal to 2 pi, so k must equal pi. Now I have to determine which trig function am I going to use. Am I going to use sine or cosine? And the key is in part A. It says, assuming that the pendulum is at the center point and heading to the right at t equals 0. That means it's starting at 0. Anytime your graph starts its period at 0, that's sine. If it says it starts at its maximum or minimum, that's cosine. So we're going to say the equation is y equals a sine of k theta. Except we're not going to use theta this time, we're going to use t, because the input is not an angle, the input is the time. So we will usually change this variable depending on what the input is. And in this case it was time, so I changed it to t. The next question you should be asking yourself is, but Mrs. F, in that last problem you put a plus or minus sign in front of the amplitude. Why didn't you do that here? Unless they give me some other information, we're going to assume it's positive. We're going to say, well, it was heading to the right, and normally the right is positive and to the left is negative. So we're going to say this is the equation. So in part B, I can determine the distance from the center at 1 second, 1.5 seconds, 1.75 seconds, and 2 seconds. Remember that you're not going to do this in your calculator unless you are in radian mode. So you're going to do y is equal to 0.15 sine of 1 pi. Y is equal to 0.15 sine of 1.5 pi. Y is equal to 0.15 sine of 1.75 pi. And y is equal to 0.15 sine of 2 pi. I mean, I realize it's pi times 1.5, but what difference does it make? So 0.15 sine of 1 pi is going to be 0. So at 1 second, it's back to 0. At 1.5 seconds, it's going to be at negative 0.15 meters. That means it's probably gone that way. At 1.75 seconds, it's going to be at negative about 0.11. And then at 2 seconds, it's going to be back at 0. The period represents the amount of time that it takes to complete one cycle. The number of cycles per unit of time is called the frequency, something that we talked about in physics. The period and frequency, they're just reciprocals of each other. And the unit of measurement of the frequency is the hertz, abbreviated to capital H, small z. 1 hertz is about 1 cycle per second. Example 6, the Willis Tower in Chicago, formerly known as the Sears Tower, sways back and forth at a vibration frequency of about 0.1 hertz. On average, it sways 6 inches from true center. Write an equation of the sine function that represents this behavior. If you're trying to envision what's happening, remember with these really tall buildings, the wind, the higher up in the atmosphere you goes, gets a little strong, and it kind of makes the building move. They design these buildings such that they can sway with the wind. If it didn't sway with the wind would knock it off. And so you probably don't want to get knocked off the top of the Willis Tower. So if you ever go up to the observation deck and go stand out on that nice glass extension up there and stare down at the city below, know that you're swaying back and forth up there, about 12 inches total. So let's go back to how we're going to write the equation to represent this behavior. So we know where true center is. Let's say that there's no wind. We're at true center. We're going to call this a sine function then, not a cosine function. Cosine function is only if I'm starting at a maximum or minimum. The average is that it sways 6 inches from true center. That means that the top of this building goes a little bit 6 inches that way, 6 inches that way. So my amplitude is going to be 6. Since the frequency is 0.1 hertz, I find the period by doing the reciprocal of that number. And if you do 1 divided by 0.1 in your calculator, you're going to find out the answer is 10. But remember, 10 is not the number that gets plugged into our equation. We have to find out what k is. So we're going to set this equal to 2 pi over k. And then I have a proportion that I'm going to use to find out what k is. And I'm going to find out k is 2 pi over 10, which reduces to pi over 5. Now again, the reason I'm going to use t is because in our application problems we normally use t rather than theta, because theta normally represents an angle, and we want to talk about the time under which this occurs. Also because hertz is a time per cycle. So I'll just assume, because I don't know any differently, that my amplitude, that my wind just kind of pushes it off to the right. So let's just say that it's 6 sine of pi over 5t. And that's the equation that represents the movement of the Willis Tower. And that is section 6.4 on amplitude and period of sine and cosine functions. We'll start shifting the graph up and down and left and right in the next section.